So guys, after the third midterm, we have two chapters left. Chapter 20 talks about more thermodynamics. We talk about some of it in chapter 6, introduce enthalpy. And so in this chapter, we're gonna learn more thermodynamic terms, mainly the free energy and the entropy of the system, and the chemical reactions that involve these thermodynamics terms. So in the last few chapters, we have looked at some fundamental questions about a chemical change. Right, so first we look at how fast it happens, right, which is related to the rate constant. Also, we look at how far does it go toward completion, which is related to the equilibrium constant. And then we look at what will affect this completion, or what happens when we change the concentration or the temperature. And so that's related to the equilibrium precision of a chemical reaction. But have you ever think about why does this change happen in the first place? Right, so what triggered those reactions? And also for some reactions, it seems that it only happen in one direction but not the other. Right, so chemists call these spontaneous reactions or spontaneous changes. Right, so spontaneous changes basically, right, so it's only happen or prefer happen in this one direction but not the other. Right, so this everything we're gonna learn in this chapter is related to thermodynamics. Right, so thermodynamics like developed almost 200 years ago, and by then scientists try to explain why a spontaneous changes happens. Right, so the theory we're gonna learn today, in this chapter, gonna help us explain why this spontaneous changes happens. And as far as we know, right, so this theories apply to every changes that happen in the entire universe. In chapter 20.1, we're gonna talk about the second law of thermodynamics, which is useful to help us predicting the spontaneous change. Chapter 20.1 is heavily concept-based, right? No calculation involved. But you're gonna see a lot of calculations later in this chapter. Right, so first, let's talk about what is a spontaneous change. Right, so a spontaneous change of a system is one that occurs under specific conditions without continuous input of energy from outside the system. Right, so it's pretty clear, right? For example, you burn a fuel, right? So like when you burn the fuel, right, the fuel become energy and water, carbon dioxide, right? So or when you push a book like off the table, right, it will fall on the floor, right? So for this spontaneous change, it might just need this a little bit push, right, just a little push to get started, right? So but during this change, right, so when this change start to happen, right, it will happen by itself without any input energy from outside the system, right? So once you light up this fuel, right, this fuel will burn until it's burned out, right? So it doesn't need to like heat it again, right, or continuously heat it when it's burning. Also, when you knock this book out of the table, right, so it will fall down by itself, right? It won't need me to push or give it any other force, right, to push it on the floor, right? So that's a spontaneous change. Right? So, but for a non-spontaneous change, it only happens when the surrounding continuously supply the systems some energy, right? It was continuously inputting this energy to the system from the surrounding. For example, if I want to push a very heavy object from one end of the room to another, I have to push it like all the way down. Right? So if I just give it a little bit push at the beginning, it just stop right? By moving just a little bit, right? It's not spontaneous. I have to push it all the way down, right? So that's example of a non-spontaneous change, right? So under given conditions, right, meaning that when this condition is fixed, right, fixed volume, fixed temperature, fixed pressure, if a change is spontaneous in one direction, it will be not a spontaneous reaction for the other direction. Right? So if it's spontaneous in one direction, it's not in the other direction. Right? For example, you gave this condition of burning this fuel, right? So after the reaction complete, right? So burning the fuel is spontaneous, right? But after it's complete, the product, this energy, this water and the carbon dioxide, it won't go back to the fuel. Right? So it won't be a spontaneous reaction anymore. You have to synthesize this fuel again. Right? Also, if the given condition for a cube of ice, right, to melt in your hand, right? So under this condition, the ice will melt, right? But without changing the condition, this pot of water will never turn back into that cube of ice. Right? So for a spontaneous reaction, right? So it doesn't mean it happens like instantaneously, right? So spontaneous is not instantaneous. Sometimes it's spontaneous, could be instantaneous, but sometimes it's not, right? So do not confuse between these two terms. Right? Some spontaneous reactions, right? For example, like aging, right, or rusting, right? That could take many years, right? But those are not instantaneous. Right? In chapter 6, we first introduced the concept of thermodynamics, right? Where we introduced this term H, which is enthalpy, right? So that's related to the energy of the system or the surrounding. And we also introduced this first law of thermodynamics, right? Which means that the energy is conserved, right? It's converted from one form to another, right? So in chapter 6, we said that for the internal energy of a system, right, could involve heat or work, right? So for the change of this energy, right, that's related to the heat flow, right, either go in or go outside, and the work, right, work done on the system or the system done some work to the surroundings, right? They both have signs, right? And we also said because it's conservation energy, right? So the change of the system will be equal to the negative change of the surrounding, right? So if the system energy increases, right, so it means it absorbs some energy. That energy is from the surrounding, right? So the surrounding will lose some energy, right? So we have this delta E of system equal to negative delta E of the surrounding. And if you separate this delta E into Q and W, right? So the sum of the Q heat and the work of the system will equal to the negative sum of the heat and work from the surrounding. Right. So because they have negative sign, right? So that means if you add them up, they're gonna equal to 0. Right. So and that change in terms of their overall change to the universe, right? The universe is the sum of the system and the surrounding, right? So the change of energy in the entire universe is always 0. So that's what the first law of thermodynamics states. Right? So but this doesn't help us determine the direction of a spontaneous process, right? For example, a lot of spontaneous reactions, right, that it obey the first law of thermodynamics, right? For example, like again, when the ice melt in your hand, right, the thermal energy of your hand, right, is converted to the kinetic energy of these water molecules, right? Because when this ice, right, become water, the kinetic energy of the water molecules increases, right? So we have this conservation of energy. Also, when you heat the fuel in your engine, right? So that energy becomes the kinetic energy, right, of the car, right? So this energy conserved, but it doesn't tell us anything about why this spontaneous reaction, right, is preferred in this one direction. Also, this change of enthalpy delta H does not predict the direction of a spontaneous reaction either, right? Or it does not predict the spontaneous change at all, right? So you might think, oh, if this spontaneous reaction need a little bit push at the beginning, that means it requires energy, right? So it must be endothermic, right? So delta H must be greater than 0. But actually that's not the case, right? So in the nature, right, there are some spontaneous processes that has a delta H less than 0, or that's exothermic. And there are also some spontaneous processes that has this delta H greater than 0. Right? For example, for exothermic reactions with this delta H less than 0, for example, the liquid water become a solid at this certain condition, right, at a low temperature, right? Because we're talking about at a given condition, right? So the conditions should be given, right? So this is actually an isothermal reaction, but at this temperature, the freezing is a spontaneous reaction, right? Also, when you burn methane, right, in oxygen, right, generate this carbon dioxide and water, that is release a lot of energy, right? So that's also a spontaneous reaction. Also, the rusting of iron, right, in the air when they react with oxygen is a isothermal reaction. Right, so for some spontaneous processes with delta H greater than 0, right, endothermal reaction. For example, in this case, right, for solid water, right, which ice become water, again at 0 Celsius, it will melt, right? When it melts, it's also a spontaneous reaction, and it has a delta H greater than 0, meaning that it's endothermic. And for any salt solution like dissolve in water, right, dissolute, right, so it will release energy, right, because you break this ionic bond. And I mean, you require energy because you need some energy to break this ionic bond, right? So it's an endothermic process. And for some type of endothermic reaction, for example, when you mix this barium hydroxide hydrate with this ammonium nitrate, right? So which is shown in this picture. So when you mix these two compounds together, it's actually very endothermic, so it will require a lot of energy from the surrounding. So you can see, right, if you put a little bit of water, right, on this board, on the center of this board, and then when this reaction happens, you place this glass beaker right, on top of this pot of water, and then when this reaction complete, you release the beaker. It turns out that this board actually is lifted together, right? It is actually stick to the bottom beaker because that pot of water already frozen, right? Because the reaction, that's those chemicals in the beaker, it will require energy from the surroundings, so it just absorb the energy from water, right? So the water become ice, so that's why they become stick together. So we just look at, right, the first law of thermodynamics doesn't help us explain a spontaneous change, and neither the delta H, right? So actually at the beginning, some scientists believe, right, delta H is related or could be used to explain a spontaneous change, but we just learned that they don't, right? So what exactly will cause this spontaneous change, right? So why this one direction uh, change is preferred, right? So then we introduce this freedom of particle motion and the dispersal of kinetic energy, right? So this spontaneous change is closely related to this concept, right? So recall those previous examples of spontaneous endothermic processes, right? So they all have this one major feature in common, right? So in every single cases, right? In every single case, these chemical entities, either the molecules or atoms or the ions, have more freedom of motion after the change. So put it another way, like after this spontaneous change, the particles have a wider range of energy of motion, right, which is this kinetic energy. So, or we can say that their energy become more dispersed, more distributed, or more spread out. Right? For example, when this solid become a liquid or become a gas, right? So we know that the molecules, right, have more intermolecular distance, right? They become more spread out, and the kinetic energy, right, it increases, right? So they have more freedom, right? The molecule have more freedom, and the energy is more dispersed, right? So also when you dissolve this salt in water, right? So that all these ions, right, or the molecules, right, will disperse into water, right, become more separated, so have more freedom. And also this um, chemical change, where when these crystalline solids become gas or ions in a solution, right, they from solid molecules, right, which has this very light, tight structure, right, so less freedom, and become more freedom and more dispersed energy of motion, right? So this gave us a hint about how to explain, right, this spontaneous change. So in thermodynamic terms, right, a change in the freedom motion of particles in a system, which is also the dispersal of their energy of motion, right? So it's a key factor for predicting the direction of a spontaneous process. Since the freedom of motion and the dispersal of this kinetic energy is related to the spontaneous change, so can we quantify this degree of freedom, right, in for a certain system? And the answer is yes, right? So imagine you have a container, right, containing some gas molecules, right? So looking at this animation at the bottom right, so let's pick one. Let's say there is one of the molecules is a carbon dioxide molecule, right? So for this carbon dioxide molecule, right, so within the molecule itself, right, it contains this one carbon and two oxygen, right? These two carbon oxygen double bonds, right? So this bond, is stretching, right? So also this bond angle is not like constant all the time, right? It changes a little bit, varies a little bit due to this motion or the stretching or the vibration, right? So, and for the molecule, it will also be traveling, right? So it's moving all around. It's not like moving in a straight line. You can bump into each other, right? Also, when it travels, itself it could spinning, right? It could spin or it could rotate, right? So there are a lot of like possibilities, right, for this carbon dioxide molecule, right, in terms of its own state, right? So imagine you have a container have 1 mole of gas molecules, right? So all the different combinations, the number is huge, right? So at any instant, right, you could have a certain combination of these molecules being in this state and the other molecules being in that state, and it's traveling in this direction or at this speed, and the other molecule is traveling in the other direction or some other speed. And within the molecule itself, it could have different parameters, right? Different stretching mode, different like bond angle, right? So a lot of things are different, right? So for each of this instant, right? So the state is called a microstate, right? Or it's also called this quantized state, right? So the more possibility, right? So the more combination, the more microstate is possible for a system, right? So when we try to quantify the freedom, right? So later we define this freedom of the system as entropy, S, right? So we use this symbol capitalized S to represent this freedom, which is entropy. So this is another important thermodynamic terms, right? After we learn entropy, right? So the in 1877, right? So this Australian scientist, right, last name Boltzmann, he related the number of microstates to the entropy of the system, right? So S is equal to K times natural log of W. W is the number of possible microstates, right? So that's a huge number, right? So consider if you only have one molecule, right? So it has a some number of microstates. But if you have two, right? What if you have one more of gas molecule, right? The number is huge, right? Also, when you increase the temperature, right? So you have more energy states, possible energy states moving more faster, the kinetic energy more dispersed, right? So there are more microstates available, right? So here the K is the Boltzmann constant, which has a unit of joule per K. K is Kelvin, right? So joule per Kelvin. And the number of microstates W has no unit, so this entropy by itself, right, it has also a unit of joule per Kelvin, right? So this number of microstates, right, can be affected by a lot of things, right? At the end of this lecture, we're gonna compare different systems with the different entropys. But right now, so what we need to know is that the more microstates possible, the higher the entropy. Right? So if a system has fewer microstates, it has a lower entropy. So have more microstates, has a higher entropy. Right? So for this example of spontaneous reactions or changes, right? So it all happens that the system has started with a lower entropy or with fewer microstates. It ended up with higher entropy or more microstates, right? So as you can see, this S is also a state function, right? So again, state function means that it's only related to the final and the initial state, right? It has nothing to do with the process or what happens during the middle, right? So the delta S, the change of entropy, will be the final, right? The final entropy minus the initial entropy. Right, so now for this reactions below, right? So we said we see the entropy, right, tend to get larger after the reaction, right? So but is it the only way we can determine whether this reaction is spontaneous or not? And the answer is no. So in the previous class, we look at those spontaneous reactions that are endothermic. Right? So we said we want a delta S greater than 0, right? We want this final state has a more freedom than the initial state. But that's actually not enough. That's not enough to determine the spontaneous change or the direction, right? Because we know that some of these isothermic processes, right? Also, this given conditions, right? Some reactions could be endothermic, right? So for if you just look at that system, it might have a delta S less than 0. Right? For example, when this water freezes at 0 Celsius, right? It could be spontaneous, but the delta S is less than 0, right? So can you say like the reaction is not spontaneous because delta S is less than 0? No, right? So we can not only look at the sign of the delta S of the system only, right? So we cannot just consider the system only. We need to consider both the system and the surrounding, right? So if the delta S preferred for the system, it might not mean that it's preferred for the surroundings, right? So when we consider whether this spontaneous reaction happens or the direction of it, we have to consider the second law of thermodynamics, right? The second law of thermodynamics states that all real processes, right, occur spontaneously in the direction that increase the entropy of the universe. Not the system, not the surrounding, but the universe. Right? So again, the universe is the system plus the surrounding. Right? So for spontaneous change, we want this delta S of the universe greater than 0, which means you want the delta S of the system plus the delta S of the surrounding, right? You want the sum of these two delta S greater than 0. Right? If that greater than 0, that means this reaction will happen spontaneously. Right? So based on the second law of thermodynamics, right? So it says here the sole purpose of life is dissipate energy, right? So at any single seconds, right? So the delta S is increasing, right? So because their reactions process happen continuously, right, in our life, and for every single processes, the delta S of the universe is greater than 0. So that value, this delta S is increasing all the time. So for both entropy and the enthalpy, like they have their state functions, right? So and also when we learned about enthalpy, we also learned this standard enthalpy or standard change of enthalpy, right? So which is related to the entropy of a compound or a process at this standard state, right? So for entropy, right? So this S, it also has this standard molar entropy, right? So here we emphasize molar, right? So it's related to the number of these molecules or atoms, right? Because this freedom, right, is related to the number of this remember this microstates, right? This microstates. So the more molecules, the more possible combinations, right? So here to standardize it, we use this standard molar entropy. So we have this S with this little circle, right? We call it naught on the superscript, right? So S naught, that's the standard molar entropy. So other than Joule per Kelvin, right? So now you involve this amount of the substance, right? The number of moles, so that will go to the denominator also, right? So for delta S naught, for S naught, right? So it has a unit of Joule per Kelvin and the mole. Right? So the definition again is the entropy of 1 mole of a substance in its standard state, right? So the standard state is basically the most stable form, right? So the most stable form. And again, the entropy and the enthalpy are state functions, right? But their values differ in a fundamental way, because for H enthalpy, there's no 0 point, right? So we can only measure the change, right? So we can only measure the change from the initial and the final state, so measure this delta H. So that's why we see this delta H of the reaction, delta H of formation, that we always talk about this delta H, which is the change based on the change, right? So but for this enthalpy S, there is actually a 0 point, right? So the 0 point actually defined as this freedom of this crystal, right, at absolute 0 temperature, right? So at this absolute 0 temperature, we assume that all these atoms are aligned like perfectly, right? So there's only one microstate possible, right? Because at this absolute 0 temperature, everything is completely frozen, like not moving, shaking, or vibrating at all, right? So there's only one possible microstate, right? So it's that it has this only one, right? W equal to 1. So if you plug that into the equation, right? So S equal to K, right? The Boltzmann constant times natural log of W. So the natural log of W, which is 1, that is equal to 0, right? So this is 0, right? So the entropy is equal to 0, right? So we have this 0 point, right? So at absolute 0 Kelvin temperature, right? So this is also the third law of thermodynamics, right? So the third law of thermodynamics means that a perfect crystal has 0 entropy at absolute 0 temperature, right? So then if the temperature start to increase a little bit, right? So if it increase a little bit, so we have more than one possible microstates now. So the natural log of a microstate will be greater than 0. Right? So the number of microstates is greater than 1, so the natural log is greater than 0, so the entropy will also be greater than 0. Right? So as you can see, the higher this number of microstates, right, the higher the entropy. Right? So to measure this, right, or to determine this, right, so we can just heat this crystal, right, or this substance from the absolute 0 temperature, and we can increase the temperature just slightly, right? So every time we increase the temperature, right, little by little, right, we can divide the energy required, right, for that change of temperature, right, over the temperature increment. Right? For example, I increase by 0.5 Kelvin, right? So by 0.5 Kelvin, so and that took me say 10 joule, right? So that means the S, right? The S at this 0.5 Kelvin, right? Because I increase it from 0 to 0.5 Kelvin, right? Is equal to 10 joule divided by 0.5 Kelvin. So this is the increment of temperature, right? So that means for this crystal or for this substance, the entropy at 0.5 Kelvin, right, is equal to 20 joule per Kelvin. Right, so that's how it is determined or quantified. Right, so normally we can do this until it reaches 298 Kelvin, which is about room temperature. Right, so the delta S, so the delta S from 0 Kelvin until this temperature, right, is the energy, right, is the energy required, right? So we add those up, right? So we add those up energy together divided by this increment of 298, right? So that will be the delta S. So normally people report the standard molar entropy, right? So at 298 Celsius, and in your textbook there is a table, right? So showing this standard molar entropy at 298 Kelvin. So this is part of the table I was talking about. It's in the appendix B, page A5 of your textbook, right? So in this table, right, I think this is only probably 1/3 or one quarter of the entire table, right? So for every common substance, either the elemental substance or the compound or the ion, right? So you have this standard molar entropy, right? So in the unit of joule per mole per Kelvin, right? So these are the numbers, and you also have this delta H of formation, right, which we used last semester. Later in this chapter, we're also gonna introduce this term called Gibbs free energy, right? So has this delta H, delta G sign, right? So that is something we're gonna learn later in this chapter, right? So when you do any type of calculation involving this thermodynamic terms, and you can refer to this table, right, looking for these constants, right, these some thermodynamic values. So the last part of chapter 21 is predicting the relative standard molar entropy of a system. Right, so basically you can compare this S0, right, between different systems to see which one give you more entropy. Right, so let's use a few example problems, right, to discuss each scenario. So in this 6 pairs, or we want to pick the one in each pair that has a higher entropy or higher freedom, right? So basically, so for A, so for all of them, you assume they have the same temperature other than E, because E has different temperature, right? So for A, we want to compare 1 mole of sulfur dioxide and 1 more sulfur sulfur trioxide. Right? So here you have a same number of moles of the molecules, but the molecule are different. Right? So for sulfur dioxide, each molecule has 3 atoms. This one has 4 atoms. Right? So in this case, we say this 1 mole of sulfur trioxide has higher enthalpy because you have more combinations of microstates due to each molecule has more number of atoms, right, than sulfur dioxide. So here, say if it had the same number of moles of molecules, right? So the more number of atoms, right? So higher number of atoms within each molecule, right? So the higher the entropy. Right? So here, when I say entropy, I mean the standard molar entropy. Right? So this is the case when you have the same number of molecules. Right, so for B, you're comparing 1 mole of carbon dioxide. This is solid state, this is gas state. Right, so this is pretty obvious, right? The gas molecules have more freedom, right? So the more spread it out, it's a higher kinetic energy, right? So they will have a higher entropy. And for C, you have 3 mole of oxygen gas and 2 mole of ozone. Right, so this is interesting, right? Because if you consider the number of atoms, right, they both have 6 moles, right? So here you have 3 times 2, the other one you have 2 times 3, so they have same number of atoms. So in this case, the number of molecules is gonna dominate, right? So for this one, we're gonna pick 3 moles of oxygen because we have more numbers of molecules. Right? So that will give you more freedom or more microstates within the system. D, you have 1 mole of KBr solid and 1 mole KBr solution. Right, so this is a solid. This is when you dissolve in a solution. Right, so apparently the solution, the KBr become potassium ions and bromide ions. Right, so they are more separated. Right, they have more freedom to move within the aqueous phase. Right, so they have more freedom, so they will have this will have a higher entropy. So E, seawater at 2 Celsius and 23 Celsius. So the higher the temperature, right, for the same amount of substance, right, so the higher the temperature, the higher the entropy. Right, so higher temperature meaning more kinetic energy. Right, so moving faster, right, so more microstates available, right? So that will give you a higher entropy. So we choose a higher temperature. Right? The last one, you have 1 mole of CF4 and 1 mole of CCl4. Right? So in this case, you have the same number of moles of molecules. Also, within each molecule, you have same number of atoms. Right? So in this case, we compare the molecular weight. Right? So the higher the molecular weight or the molar mass, right? So the higher the entropy. Right? So this is heavier, right? CCl4 is heavier, so that will have a higher entropy. Right? So there are 3 homework problems. Right? So it's either related to the spontaneous reaction, right? Second law of thermodynamics, and the comparing the standard molar entropy of a system. So as I said, you don't need to turn in the last homework, but working on the homework will definitely help you preparing the final exam, right? Because you're gonna see similar problems in the final exam. I will see you guys in the next lecture.